Okay, hello students, welcome back. So what I'm going to go through in today's video are three forms of the Biot Savart Law. Sorry, I had a little spelling error there. This would be a T there at the end, so some French. The Biot Savart Law here is going to be the topic for today's video. Now this formula that we're going to cover today is very important for determining the magnetic field that is produced by current carrying wires. So wires, as we know, they carry current and they create magnetic fields, right? So they induce some magnetic field due to the charges that are moving inside. This formula describes the amount of magnetic field total that is induced when we have current running through these wires. So for this formula, this is the kind of the base form of our formula right here. This is the Biot Savart Law here. What we're going to do today is we're going to adapt this into three different kind of simpler forms that are a little bit more situational, but they're easier to use, right? So again, we won't be working with the integral directly, but to kind of point out what is involved here is that we're going to have some wire, and we're going to take some length of wire, okay? And we're going to look at how far away we are from the wire, right? So if I had a wire right here, let's say I have some entire length of, some small length of wire, and then I'm pointing in some direction. Let's say I want to know the magnetic field right here. So right here, what is the magnetic field, okay? So what we're going to do is you need to know basically how far away this point is from the wire, the length of the wire that we're looking at that's producing some magnetic field, okay? And then what you need to do, of course, is you need to integrate over the entire length of the wire, right? Because let's say I have a small length of wire here. There's current going through it. Well, this is creating some magnetic field here, right? But then also, here I have an image showing here. So let's say that right here, I have a point of wire, a small length of wire, and it creates some magnetic field out here at this point. But there is also going to be magnetic field that is induced from this point here, okay? Let's kind of use here some small vectors, kind of pointing out this way, or this point here, out here to here, or this purple labeled point right here as well. Okay, sorry, just trying to kind of point them all, towards this point. They are all going to create some contribution. So the integral here is just saying, once you find the contribution from one small segment, some very tiny segment of wire, you're going to integrate over all of them, add them all up together, right? But this can be a little bit tricky for us to do, of course, throughout our entire length of wire. So we're going to create three different scenarios where we're going to kind of inspect what this formula will tell us. So the first one is the simplest. The first one, what we're going to do is we're going to say that our distance is very far away compared to the length of wire. And what this is going to do is we're only going to be looking at one small segment, and we're going to be looking at something very far away. So we're basically going to reduce this down into like a single point, right? Imagine if my length was too long. For example, if this was my length right here, then this entire length has different radius values that you still have to integrate, right? But if we make this small enough, and if we put this point far enough away, then we have essentially just one radius value. So it makes it a little bit easier. We kind of don't need to integrate here. So what will happen if I have a very small length of wire, DL, and my radius is much larger than this small length value, I can reduce this down to just, instead of an integration, kind of just a single data point. And so when we do this, I have here a little transformation that I've done. Don't worry about this. We won't be doing this derivation. What you guys will do is you'll just apply these formulas. But just to show you where they come from, we change this cross product into dl sine theta. And then for a very small dl, it's going to be delta L. Okay? And then this will be the form for our formula. So what this formula, this is the first form right here of our formula. This is number 1 here. It kind of goes with the label right here. This is the magnetic field that is generated due to a small segment, right? Oops, sorry about that. And my screen kind of flipped over on me. So this is due to a small segment of wire, right? So this is a small segment of wire that's going to create a magnetic field at this point. So that is what this formula will help us to find. So best thing we can do here is we can apply this formula directly. So let's go ahead and grab this formula right here and bring it down. And we're going to do an example here together. Okay, so go ahead and follow along and see if you can, apply this formula. This will be kind of going through and finding each of the variable values and plugging them in correctly in our formula. So the first thing here that we need to find is going to be, we're going to do part B in this example right here. We're going to do part B. And so there are a few things that we need to know. First of all, I need to know what the current is. Oh, sorry, here I have some values that got cut off. Okay, I need to know what the current is in my wire, and it actually tells us right here in the problem. So this is the current. There are 10 amps of current in my wire. This is 10 amps. Okay, and then we're going to look at here, kind of, if you look through the problem, I have 10 amps of current going through my wire. And if I have a small segment here, this small segment right here of 0.5 millimeters, okay, then what is the magnetic field at this point right here, point B? Okay, so point B. So we can go ahead and set this up. So there'll be a few steps for us to take. The first one is going to be using here, finding delta L. So let's go ahead and find delta L in our formula. We know what I is. Delta L, remember that should be this point right here, which is 0.5 millimeters, 0.5 millimeter. Remember to convert this when you use it in your problems. So this is going to be 0.5 millimeters, which is 0.5 times 10 to the minus 3 meters, right? Okay, so we have this now. Now the next thing that we need to find, these two are a little bit trickier. I need to find the angle, and I need to find my distance, my R. My R is going to be the distance from this point right here to point B. So let's see if you can do this. Go ahead and you can pause the video now and try to see if you can find, I think, this distance right here. So what is R equal to? So if you did this, there are a few ways I can do this. One is Pythagorean theorem, right? I can do R is equal to the square root of 3 centimeters squared plus 4 centimeters squared. Okay, I can find this. If you also know, this is a common triangle, so I have 3, 4, 5 triangles. So, kind of using a little bit of math trick here, we can skip this step. This will be 5 centimeters. Okay, so my R will be 5 centimeters, and this goes into my formula right here. So this being R is 5 centimeters, which remember is going to be 5 times 10 to the minus 2 meters. Don't forget your conversions in these problems. Okay, and then the last one, you can use, since we know all 3 sides of our triangle, you can use any of your trigonometric functions that you like to find this angle right here. So this is the other slightly tricky thing here, is what is this angle? Okay. Okay, I want to know what this angle is right here, but this is kind of outside of my triangle. But just to give you guys, don't freak out, right? So we can still do this. This is actually, if I were to draw out the triangle this way here, and this way here, okay, then this is still 3 centimeters, right? It's 3 centimeters on either side, 3 centimeters. And this is still 4 centimeters. So it's the same thing as my triangle here above. 4 centimeters is still here, 3 centimeters is still here. So you can find this angle. So one that I'll use here that I use pretty often, will be tangent. So I can say here that tangent theta is going to be opposite over adjacent, right? Which here means tangent theta is going to be 3 centimeters divided by 4 centimeters. Remember, opposite to my angle and adjacent to my angle, okay? And the last thing, of course, I want theta. I don't want tangent theta, right? So I need one more step here, which is going to be to cancel or take the inverse of tangent to cancel it on both sides. And the way that I do this is I actually take the tangent inverse of both sides. Tangent inverse, and this will give me the angle that I want. This is theta is equal to tangent inverse of 3 over 4 centimeters, right? But so here we go. So to get this with our calculators, we'll kind of check this out. So here, this is going to be my angle is tangent inverse. We'll do this kind of together here. This should be 36.9 degrees. We're going to say 36.9 degrees. 36.9 degrees. Okay, so pretty good. So we can plug this in here as 36.9 degrees. Okay, all of this was really just to find all of the information and set it up. So it seems like we've done a lot of legwork here just in the setup, but we haven't actually gone back and solved this problem, right? But this is actually the easy step. If we kind of go in now and try to solve this problem, it's quite easy. So let's take everything that we've done here. I'm going to do this in green and just set up our formula. My magnetic field should be mu naught over 4 pi times, times my current, which is 10 amps, my delta L, which is 0.5 times 10 to the minus 3 meters, and I have the sine of 36.9 degrees. And then I have here on the denominator of this, I have r squared, which is 5 times 10 to the minus 2, all of that squared, okay? So at this point here, we're ready to solve this. Remember, just as a quick note, that mu naught right here is a constant. This is the permeability of free space, and this is equal to 4 pi times 10 to the minus 7, okay? So we can plug this in as well. All right, so at this point, we have all of our values here to put in. I'll leave this up to you guys to find our final answer here, but this is just kind of a walkthrough of how you would do this. Now, for part A, as a separate example, would be much simpler, because in part A, if I wanted to find the magnetic field at this point right here, then the only thing that would change would be the angle. First of all, my angle would be 90 degrees between the wire and part A, okay? So this angle would be 90 degrees. And then, of course, the distance from the wire to part A, you would just need 3 centimeters. You wouldn't need to do all this trigonometry, right? So you would just use 3 centimeters. And that would be the only thing really that changes between part A and part B. So you can try both of these out and see if you feel comfortable using this formula with either approach.